a lot to the organizers for organizing this workshop in this wonderful place and giving me the opportunity to present our results from the University of Virginia. And I'm following up on the microscopes again, and I will present our kind of pretty recent microscope that we set up at the University of Virginia. Before I start, I kind of want to go a little bit through some general ideas of quantum simulation. And in particular, I kind of want to collect a couple of ideas where quantum simulation is actually a challenge for the theory and where actually experimental efforts are at the moment. So I picked here more or less randomly 4 topics. One is the dynamics and time evolution, and we did some experiments when I was in Munich on many-body localization. There's this experiment from Princeton I was involved in on transport in systems, and that's certainly something one can kind of continue working on. Unfortunately, this is kind of a pretty challenging experiment, but it's certainly more parameters that we are interested in measuring. Then there's other directions that are very challenging also for theory. One was already in the podium discussion about SUN systems, so kind of increasing the number of on-site states in these Hubbard systems. And there's a lot of interesting physics going on, and that's also kind of one direction we are thinking about. Then another direction are longer range systems, and we're kind of also going a little bit in this direction. So I was involved in some of these Rydberg tracing experiments and Rydberg excitation. So we looked at these Rydberg excitation and lattices and saw the correlations between the excitations. And now there's like a whole bunch of different platforms based on molecules, magnetic atoms, and so on. Today I will more focus on the direction of frustrated systems. And so here we are looking in our system at this triangular system. And there's the challenge essentially comes from the fact to the theory that there's a large constant degeneracy. Okay, just a little bit of an overview of what we do in Virginia. So we have mainly this microscope. Then we had some experiments. I was still involved in Princeton on the Rydberg tracing. We did a little bit of theory on this triangular Hubbard, setting up now U experiment and some other side projects. Today I will focus on this microscope, on the triangle lattice, and will show maybe 2 slides on what we are doing at our new turbine experiment and what we want to do in the future. So just a little bit of an introduction to our view on the triangle lattice and what is interesting about it. So in the end, we have seen essentially the idea already 2 times, but here again, the idea is essentially that we have this Hubbard system that has naturally antiferromagnetic interactions on nearest neighbor sites, and then the question is essentially how do you find a state that satisfies that. In the end, it turns out essentially you can find this 120-degree order, but generally, essentially, you find a lot of states with equal energy in a large ground state degeneracy. And so one approach to kind of try to construct some state near the ground state essentially is looking at these singlets on neighboring sites. So you can figure out that pretty easily that these reduce the energy. And then you can say, okay, I can kind of cover the whole lattice with these singlets. And then this kind of leads to a whole bunch of states that all end up with the same energy in good approximation. And so they're all the same energy here. You can kind of find all kind of different coverings. And then even if the singlets are over longer distances, that's also an option. And then the idea is kind of if you take the superposition of all these states, you kind of end up with some kind of spin liquid-like a state. And so it turns out this is actually the real picture, but it's maybe a good thing to have in mind as like a possible idea how these states could look like. And so our motivation is essentially it comes from the analogy of our systems with condensed matter. So there's essentially these triangular Hubbard systems, which are some organic compounds, which then can be kind of modeled by a triangular Hubbard system. And we can then realize this triangle Hubbard system with ultra-cold atoms. On the other side, there's also our kind of longer-term perspective to look at systems like the Hubbard, which is kind of the ideal system to look at spin liquids, and that's kind of where most of the condensed matter work is claiming spin liquids is done, and there you could kind of try to realize this Hubbard model. So just one slide on the definition of the model. Of course, you have seen that already several times. So we have essentially our two terms of tunneling of fermions. So we have two spin states of fermions, tunneling with T, and then the interaction of two different spins on the same side. So that's kind of our cartoon of the interaction and the tunneling. And so we can kind of directly look at these atoms, and then, what is kind of the expected phase diagram? And then essentially, because it's a triangular lattice, there's a little bit of different things going on. So in principle, you have this T prime that can be different, but we mostly look at the central line where T prime is equals T. And then essentially you see in this diagram from the calculations that you expect quite a few things going on. And in particular, what we wanted to look at is essentially this regime where some people seen the chiral spin liquid, and also the spiral state is already kind of a little different spin ordering than what you have on the square lattice. And before we kind of mainly COVID times, we worked a little bit on some theory to kind of see ourselves what we get out. So we worked out one of these numerical quantized expansion, and that's a work by one of my undergrads. And he kind of went deep into that. And I mean, just as an example here, we can essentially pretty nicely calculate these spin-spin correlations versus temperature, and here we have a comparison between kind of these more established DQMC calculations, and we get essentially with an error bars the same here. Yes?
Just a question. So the SZ correlator is between which sites?
This is nearest neighbor spin correlator.
Thank you.
So for this, it's just, I just want to advertise that it matches, but I go a little bit more into detail afterwards. Yes, so in conclusion, essentially here, the story is at very strong interactions, so in a relatively large U over T, this an LCE technique works very well, and it's calculationally faster than the QMC. And so a little bit more advanced slide is here. We kind of try to push that a little bit and try to follow some ideas other people came up with to this look at the mod transition. And so the trick with NLCE is that you can very well calculate essentially a lot of parameters versus chemical potential and temperature at the same time. And so here we can essentially get data that takes quite extensive calculations in QMC pretty fast. For example, we can determine the compressibility versus temperature at different interactions, which requires also different chemical potentials in the end. And then what we did is we followed some ideas that have been shown with the Schauss method, and used some gap model here. And this kind of reasonably agrees. And then if you can look at fit this kind of gap, we can do some kind of scaling of the gap. And if you believe that this is linear, we can kind of make some prediction for this phase transition. I have to say this is consistent with the Schauss method, but not consistent with the METS. So I think there's still some kind of question. What is actually the phase transition? Maybe there are several. So I think this is still an open question in the end. What is actually happening in those triangle letters?
I'm a little confused by one thing. At high temperature, shouldn't compressibility behave like 1 over temperature? I think that's because we are at temperatures above the hopping, right? So
this is temperature above the hopping. So this is just the n by the mu. Mm-hmm. I don't know. There's a different
maybe we can discuss this offline.
Definition. So this is the n by the mu.
Yeah.
What we're showing.
Okay.
We can discuss how that.
And can you say again what NLC acronym stands for? NLCE stands for what?
Numerical link cluster expansion.
Yeah, okay.
So it's a cluster expansion. So you essentially just take all sub-clusters of the lattice and perform exact diagonalization. So we just do complete exact diagonalization on that. And we go to ninth order, which means we diagonalize up to 9 side clusters on just all of them. And just one comment here that we also looked a little bit. So we kind of dug out the data again that we had in this paper when the paper from the Greiner group came out. And so we even did essentially scans versus density. And you can see here, this is our NLCE data, is the blue points, and the green is the experimental data from the Greiner group. And you see that fits pretty well here. So we can even do a little bit of finite doping calculations in this NLCE. You see on some side, the convergence is worse than in the other, but this is kind of what you have to live with these CS expansion techniques. So sometimes, in some regimes, the convergence is rather bad, in others is very good. Okay, so what are we interested here in? And I think one of the main new things that might happen in the triangle lattice is essentially this non-collinear spin ordering, which is essentially measured by this triple product of the spin. So that has been seen here in these theory calculations, that essentially in this U/T regime between 9 and 10 or so, you get essentially spins that are not either aligned or co-aligned, but they kind of have some angle between them. And then if you put 3 on a triangular plaquette together, essentially they enclose some volume. And so that's kind of interesting, and our kind of long-term plan is to look at that in the experiment. And there's, of course, different approaches, but I mean, kind of the straightforward idea would be to essentially think about this, what you can call the chiral ordering parameter. You will figure out that this is essentially not necessarily the right thing to look at, because there is essentially some kind of staggered ordering in that. So if you average over it, it might be 0. So what you have to look at is essentially some correlation between plaquettes. And then there's different ways to do that, either to apply essentially some symmetry breaking, which is often done in theory calculations. But it would be nice to essentially do it in the experiment. And that idea here is essentially you can kind of multiply this out. In the end, what you have to do is on the experiment side to measure spin operators in different bases on different sites. So what you would need is essentially local single qubit operations on the different sites. So that's kind of the challenge here on the microscope side, is essentially to implement these local spin qubit rotations. Okay. And then just the other thing, a little bit different view that's interesting, is this kinetic frustration. And so here you have seen it before, that essentially if you have think about a spin polarized system and you have hopping in there, that on a square lattice essentially all paths have odd length. And so the total sign is the same in each case, while on the triangle lattice the path length is different. And in that case, essentially, you can get this destructive interference. And the main point I want to make, which is coming from this paper down here, is that if you plug in essentially one spin impurity here, that the two paths are not leading to equivalent configurations anymore. And then if they lead to different configurations, the interference is broken. So that means you get a stronger you get a reduction of the suppression. So essentially, the particle hole state here can delocalize more in the presence of the spin impurity. So that means the kinetic energy is lower, and so you get essentially these kind of bound states that scale with the tunneling. So that's kind of the interesting thing. With this introduction, I kind of wanted to switch over to some more experimental part, and just showing essentially all the quantumized microscopes where we've heard. The nice thing is that you can image all the individual atoms here in the different systems. And what we did in Virginia is essentially we did a microscope that has now the feature that we have a triangle lattice and a square lattice. Where the square lattice was more like we just added it because it was easier than the triangle lattice. The nice thing about our triangle is that we can kind of we have a spacing of 1 micron here. We can see all individual atoms completely separated in the picture. And we can now produce mod insulators in both of them. A little bit of the status of the field on these triangular lattices. So there's a couple of experiments that do this with bosons. And then recently there's essentially 3 experiments mostly now that have alter-called systems in the triangular lattice. Our experiment, the group in Marcus Greiner's group in Harvard, and the Princeton group, Basim-Baker. And there's, of course, earlier work on frustrated lattices. and also different kinds of lattices. Just to give a little bit of an overview, the earliest, I think, is from the Hubbard group with BSCs in this triangular lattice. And then there's nowadays also known how to create cargo mill lattices. A lot of people thinking about microscopes for these cargo mill lattices. Unfortunately, this configuration that is used here is kind of extremely challenging for a microscope. And then there's also implementations for the leap lattice, and we have seen in the talk from the Quiner group about the implementation of the leap lattice. Just a little bit of general what is kind of interesting about the microscope. And the nice thing is essentially that you have all these side-resolved observables, so we can get the full density. We can get the density of only single occupied sites, so we can get kind of the full distribution function on the site. We developed the technique to only get the doublons in Princeton. That's nice, because then you can kind of go with a single, can kind of combine these all to get everything. And then, of course, the nice thing about this single-shot imaging technique is that you can get, in principle, arbitrary correlation functions. And usually we look at these connected correlators here. And you can have essentially, you can plug in essentially any observable you have up there into the correlator. And then the question is mainly for the theory, which of these correlators are actually interesting to look at and which are not, because some of them look pretty boring if you calculate them. And so it's then the question. So we mostly focus on these spin-spin correlations, but there's a lot of other correlators that may be interesting, but they kind of, it's kind of a really large number. And so our picture here is essentially that we have essentially our wave function, and we kind of project to one of these configurations, and then take a lot of statistics to reconstruct essentially what happened here in this many-body wave function. It's kind of an idea. So experimentally, this is all not completely straightforward. Our triangular microscope has kind of a complicated structure here. And so there's different ways to do the triangle lattice. Our approach is essentially to have 3 beams in a tripod configuration. And these 3 beams are sigma polarized. So if you do the calculation, you can convince yourself that this leads to a triangle lattice interference. And the angle has the advantage that you can kind of make the spacing a little larger, which can be simpler for the imaging. And because we need very high power for the imaging, and we do the imaging and the physics in the same lattice, which is not the case for the other for many of the other experiments, we essentially recycle the beam 3 times, and that makes, of course, the optical setup somewhat involved. But it turned out it's like not too bad in stability, but it's very challenging to cross these 3 beams in the center of the chamber. Okay, just to show a little bit of a picture how this looks like. The chamber itself is relatively straightforward, but it's a lot of optics and, of course, some lasers for laser cooling. And so the main difference to the other microscopes for us is essentially that we actually see this hexagonal structure of the atoms directly in real space in the picture. The other experiments have essentially some kind of squeeze structure. And the question is now, what does it help you? For the Hubbard model, it doesn't really help you, but we are thinking about things like, for example, Rydberg tracing or so, and then you actually want the same spacing between the atoms. For other things, maybe there's some other ideas where you actually need same spacing. Might be if you want to run some waves or so over it, it might be good to have essentially equal spacing in different directions. So I wanted to go through a couple of technical details here just to give a little bit of idea that was not in the previous talks. So, of course, if you have a different lattice structure, we have to kind of figure out how these atoms are organized. Just to give a little bit of an idea how this works, so essentially kind of pick individual atoms and then project them on a plane so we can kind of measure the effective lattice constants in all directions very precisely. Then the other thing that's very important here is we do some Raman sideband cooling, and so what matters is essentially this is a Raman sideband spectrum, is essentially the frequency, the oscillation frequency of these lithium atoms in the trap, and you see essentially our lithium atoms oscillate with like between 1 and 2 megahertz for us, which is a pretty fast oscillation for some kind of atom like that. And this is kind of what you need. If you get this, the imaging is kind of rather straightforward. And so this is just a typical picture. An overlaid is essentially these small dots are the points that we kind of, by fitting these atoms and so determine. So this is the lattice sites that are kind of overlaid. And you can see that obviously all the atoms sit exactly on the lattice sides. And then you can kind of extract other things like the size of the atoms that you see is essentially just a Poinsett function given by the optical system. And then if you kind of plot a histogram of so you fit like Gaussians to each side and get essentially a histogram of these amplitudes of the Gaussians, and then you can see nicely the splitting of the 0 and 1 atom peak. So you can kind of see we actually have single atoms here. That's just some technical details. And in addition, what we kind of put a lot of effort in is we have this kind of somewhat unusual triangle lattice. So we kind of thought quite a bit about how to calculate and calibrate the Hubbard parameters. So there's the interaction and the tunneling. And so what you can do is essentially calculate the band structure that you get from your lattice configuration. And you can calculate the one-year functions here. And then from the one-year functions, you can determine essentially the interaction. And so, it turns out it's surprisingly hard to get like well-converged one-year functions for this because it's a non-separable 2D lattice. But we managed to do all of that and kind of checked all the parameters here. And so we can see that we can kind of use lattice depth modulation spectroscopy. We find essentially these higher bands here, in our case P and D bands. And then can kind of from that and into combination with the band structure calculation determine the tunneling. And then we have two ways to determine the interaction. One is just modulation spectroscopy, where you see nicely how the interaction changes with the scattering length, which is tunable by a magnetic field in our case. But we can also use like radio frequency spectroscopy, which is a little more precise, and that also is consistent with these with these measurements.
Peter?
Yes.
Which P band is that? Didn't you have multiple?
There's multiple. I think in our case they're overlapped. So it depends a little bit what kind of lattice you have. I mean, there's also these two D bands that are overlapped.
But like, the Z direction would be very different, right?
At the C direction, you don't see in this.
So this is just the in plane.
Actually, yeah, this is just the in plane. So if you modulate in plane, you don't need to see the out of plane resonances usually. So out of plane, that is kind of decoupled. In our case, it's a separate lattice, which is also, it's not. I mean, this is like non-separable, and the third direction is just separable. So that's kind of trivial compared to that. Yes?
How deep is the lattice in the right-hand plot?
In the right-hand plot, in this one?
Yeah.
It says it's 9.7 or so recoil. You have to be a bit careful with the definition of the recoils, because there's the recoil that's related to the spacing of the atoms and the recoil of the light.
Is the broadening in the inset due to tunneling, or is it a Fourier thing, or?
This is, so the problem with these kind of spectroscopy is, that's why they're not so precise, is that the tunneling broadens these resonances quite strongly. And if you don't have tunneling, you don't. So this technique relies on the atoms hopping on top of each other, so creating doublons. And of course, if you don't have tunneling, you don't form doublons. And if you have tunneling, you get a broadening. So this spectroscopy has some kind of fundamental problems getting narrow lines. And so if you do the microwave spectroscopy, we get much narrower lines. So in the end, I would say, the radio frequency, the radio frequency is essentially much better to get precise values. So you do that essentially in a very deep lattice, determine interactions, and then you scale back to low interaction, low lattice depth. So this one is just nice that you can directly see that. So it was kind of, you can directly see that with a relatively simple technique. Okay, good. Then what can we do? I mean, the main thing we did up to now was to show that we actually have a Hubbard model in our system. So we get essentially these mod insulators where all atoms sit next to each other, and we have some, of course, fluctuations and thermal holes. And then if you go a little higher, we can essentially start to get W-occupied sites in the center, and in the imaging, these W-occupied sites get lost. So we get this hole. And you see our system sizes are not particularly large in this triangle lattice. But we can get essentially sizes on the order of like a few, 200, 300 atoms here. And then what we did is essentially here is to essentially compare the experimental data for different atom numbers here with the theory calculations. And this is essentially then the full theory calculation. And you see these systems have a lot of fluctuations, which are partially thermal, partially quantum. And then what we compare is essentially over the radius here, the density and the variance of the density. And we can see that essentially for all of these systems, we are mostly fitting the whole cloud with the theory. So we can see that we are essentially consistent with the NLC and QMC calculations. So that's kind of so the calculations fit anyway with each other, but we also see that we can fit essentially the whole cloud, which means that we are pretty close to equilibrium here, at least in the density. Okay, good. Then the next step on top of that is to go beyond the density. And so we started with the kind of standard way to measure spin. And the standard way to measure spin is essentially to just have this system. Then you kind of rewrite your spin-spin correlator in 2 terms. So this is kind of what the other groups in Harvard and Munich are also doing. And then you essentially end up with 3 terms. And these 3 terms you can measure separately as correlators. And to do that, you essentially need to remove your doublons. In our case, we sweep over Feshbach resonance. And then you remove either the one spin or the other spin. And then you just take statistics on these different pictures. And then you plug that into your formula and get the spin-spin correlator. So that's kind of the way without full spin-resolved imaging. And what we get here is essentially in the experiment that we get anti-correlations of the spin on all nearest neighbor sites. But unfortunately, our temperature was here not low enough to see anything on the next neighbor site. So the main difference here to a square lattice, what we see is essentially that instead of getting the staggered pattern and some positive and negative correlations on nearest neighbor sites, that all of them are negative. And we can see that from GQMC at comparable temperature, we see essentially that we kind of don't expect anything beyond nearest neighbor. Okay, how do you do the temperature? So we kind of follow the same idea that the other groups are doing. So essentially what you do is you have a calculation of the spin-spin correlator versus a temperature. That's kind of what I showed in the beginning. That's why these calculations are important. And then we have essentially our correlations. In our case, unfortunately, the error bar was pretty large, mostly also technical noise. And then we essentially get some temperature range and some error bar here. And so at the moment, our temperature is still kind of pretty high. And so we kind of also are working on reducing the temperature. In particular, what we also did is we had like some trouble getting this pushing reproducibly to work reliably. And so we worked on implementing the spin and density resolved imaging. And so here the idea is you kind of want, if you want certain correlators, for example, correlators between spin and density, you need to measure essentially if there's a hole and a spin at the same time in the same system. In our case, how we do that, so this is just a picture from the side, is we kind of take the cloud and apply gradient, and then one of the spins goes up, the other one goes down. We do that in the lattice, so there's essentially a single particle problem. You have essentially each tube, there's 1 or 2 particles in there, one goes up, one goes down. And then once they're there, we kind of capture them with some light sheet, and then we take images of them simultaneously. And you just have essentially 2 imaging systems that image your system on different places of the camera. And then you take one picture, and this is kind of 2 spots of the camera. And then you see that you have essentially these 2 spin components. And then you can kind of reconstruct the occupation in the lattice and then kind of recombine them. And then you get essentially the full picture of the density. So you see all the holes, the spin ups, the spin downs, and the doublons. So currently, so this kind of worked only a couple of weeks ago. And so now we're kind of working on using that for actual measurements. And so we have a little bit of an update on the temperature. So we kind of, in the end, that's kind of what takes the most time in the experiment. So we spent essentially a year optimizing that. And we managed to reduce it by like maybe 0.25. And so now our next steps are essentially reducing this temperature a little bit more. So at the moment, we get essentially next neighbor correlations on the square lattice. And unfortunately, these optimizations take a long time in the experiment. And the other experiments had a lot of time up to now to optimize that. So what is kind of the story now? So essentially what we have is we have now a system that has a triangular and square lattice mod insulators. So we are still kind of investigating what can we do if having both. And we can measure spin-spin correlations also with full spin density resolution. And what we've been working on lately is on single site addressing. So I have a little bit of a teaser up here where we essentially try to make a line. So we kind of showed that we can get, in principle, a single site line resolution at this point. And then we're kind of thinking about these other ideas. Essentially, yeah, these spin hole correlators, we could kind of do similar measurements as the other groups, but it would be nice to find some other ideas here. And then another plan here is to use this spatial light modulator to implement the idea of blocking out sides in this triangle lattice. And in the end, this is just a regular tweezer array that we would need to essentially create this Kagome lattice. Yeah, before I finish, I just wanted to shortly mention our new experiment. So this is kind of a little different system. We also plan to use fermions, but it's in a way of tweezers with ytterbium. And the idea here is to essentially kind of create some slightly different systems. We essentially have one fermion per tweezer here. And of course, these tweezer systems have a lot of progress in recent years, and there's a lot of techniques to essentially realize spin systems, realize very high fidelity entanglement operations. You can kind of think about and dream about like doing essentially many body systems where you can kind of measure something in the middle of some dynamics or so, and things like that. And so but these systems still have, suffer from a couple of problems. And one thing we wanted to attack is essentially that typically your vacuum lifetime is not incredibly long for these systems. And it's just this simple story. If you have some lifetime for an atom and you put many of them, you essentially get the probability of the number of atoms. And so the probability to keep some array of many atoms for a long time is kind of low. So if you want to do something with whatever 10,000 atoms for an extended amount of time, you essentially need better vacuum. And then there's, of course, other things. A lot of it is related to noise of lasers, which is something we are also fighting all the time. So that's a separate story. And there's, of course, the story with black radiation. And kind of by going through these two things, essentially we kind of decided we want to put this thing, this ytterbium tweezer array in a cryostat. And we have some other ideas, but at the moment, what we kind of think about is essentially that we could kind of actually use direct interactions between atoms to bring them together in tweezers, to entangle them, and then pull them apart. And so the nice thing about this ytterbium is that you can have essentially state-selective potentials and can kind of move them state-dependently. And now this is kind of would be a nice system to play with, and maybe one can even do some kind of fermionic experiments with this at some point.
But when you say state-selective potentials, this is the ENG states, or actually?
Yeah. So you have to go to the ENG state, to the metastable state. So one of them, the green or the blue, is the metastable state. Yeah. Okay, and yeah, just a little status on that. So we built some machine, try to keep it reasonably compact, and it's still in progress. So we just have some laser cooling up to now. Okay, with this I want to conclude. So this is the people in the lab that actually do the work, and work with a lot of undergrads, and and the funding is of course also listed. And thank you very much for your attention.
Yes, thank you for this wonderful talk. I'm pretty excited that you can actually have the prospect of measuring this chiral correlators or even the chiral operator. So just one comment, like the paper you quoted by Aaron Sass, they propose a chiral spin liquid. Yeah. They give an estimate for the gap, and that's like I think 0.006 units of the hopping. However, this gap, we have some numerics. If you put an orbital magnetic field, this can get actually quite sizable. Yeah. And so the numbers are actually, I think this can get off the order of maybe half J. So if you have U over T equal 8, then you are maybe J 0.5. And if you can, I don't know, if you then get to temperatures of 0.25 J, this would actually mean you could realize maybe a chiral spin liquid. No? The question is whether you can rotate, I guess.
The dream, I mean, this rotation will be mostly a technical challenge in the end. This will be kind of hard to implement, but it's kind of a technology that is that is possible, I would say, within the next years.
Anyway, measuring this correlator, I find this really exciting. But if one, I think this could actually be a route to maybe a chiral spin liquid.
Yes. I mean, it's a route to actually measure something that you want to know for these. And also, I mean, the story is that even if the gap is small, I mean, you expect something at finite temperatures in terms of these chiral correlators. And it would be kind of similar to the antiferromagnet. I mean, the correlations start before you actually hit the transition. And so the hope is that the question is how this decays. And I think there are not so many calculations at finite temperature for these chiral correlators. I mean, I didn't find much.
We did some published.
You did some, yeah.
But I'm just saying, like, this gap can get quite sizable if you put an orbital magnetic field. So it's not hopeless.
Yes. The question is, how do you do the orbital magnetic field? That's of course experimentally quite challenging. But there's some experiments from the Kreiner group that show that it works, that you can get magnetic field.
Beautiful. Thank you.
So
but to follow up on that, so what is your plan? How to measure these XYZ type operators? You really need to come in with like individual addressing for spin rotations?
I mean, the straightforward approach would be to put a Raman laser system on a DMD and send it to the atoms. Of course, there might be easier ways to do it. That's kind of the question.
Okay.
I'm a little confused. What magnetic field method you're thinking about that you think is compatible with your system? Could you say that again?
Which magnetic field?
Yeah, how would you apply a field in this?
An orbital.
Yeah.
I mean, our system, we didn't think exactly about it. I mean, but you would probably have to find some scheme with like some side offsets and then do density-use tunneling or something. The question is, I'm not fully sure if you can get, and you might end up with a staggered field in many configurations, but I mean, there's schemes for the square ladders that they're worked out, so I think some of them will work in some configuration of these triangle ladders, for sure. It's just a question how hard is it, and is lithium the right choice? It's also a completely different question. Probably want different atoms. The cryogenic is not there yet. So at the moment, the chamber is a little bigger, and the cryostat will essentially enter from the side. And the idea is to have essentially just a copper box that is cooled, and the rest of the chamber is at room temperature. So you kind of try to keep the cryogenic part as small as possible, because the smaller it is, the less heat you can catch.
So one could sort of try different calculations to see variations with the temperature. But from the experimental standpoint, what are the simplest things to control to tweak the system? Around.
Can you use your seat mic, please?
I don't have a.
Okay, so the question was how to tune the.
Basically, I'm sort of asking for some feedback, I guess, to theory in terms of what direction to explore. What is your easiest parameter experimentally? What is your easiest direction to tweak? Then
for the triangle ladders,
for your setup.
Yes, I mean, what's easier to tune for us is essentially tunneling, interaction, density, spin imbalance.
Tunneling. So you showed the T prime, but T prime is not. Is it can you dial it?
Yes, so that's so we know that we can dial T prime, but it's
in the triangular
in the triangular lattice. I mean, we have these 3 beams that interfere, and if you change the polarization of these 3, you have quite a lot of degrees of freedom. So we kind of did some, pretty extensive search what we can do with this. So in principle, if you do put arbitrary polarization of all the 3 beams, you could kind of go T prime for sure. Maybe you can even. We couldn't figure out completely if you can get all 3 tunneling combinations, but you can also get 3 different tunnels in certain configurations. So there's a lot of options to change the tunneling in this triangular system. What's harder, of course, is to introduce new tunnelings or so. Then you have to think about, then maybe some of these other lattices that are more flexible. Yes, and of course, artificial fields is kind of hard in particular for lithium. So that might require just different atoms.
So, Peter, I certainly agree with you that one of these kind of spin liquid physics is kind of the holy grail, but there's also some interesting physics which is perhaps reachable already at higher temperature. For example, with Alex Vitek, we have this paper in which we show that there is the so-called Pomeranchuk effect happening, where the double occupancy as a minimum as a function of temperature.
Yes, we looked a little bit into that. I mean, it looks like it's almost reachable with the temperatures people have.
Yeah.
I mean, it might be that the other groups are already at the temperatures where they could be able to see it. Here, I think, is slightly too high in the temperature.
You're getting there, I think.
We're getting there.
Where the minimum is supposed to be.
0.2 per year or so.
Other questions? Okay. If not, let's thank Peter and all 3 speakers.